How's it going, guys? Today we're going to be going over 9.2, day 1. We're going to be looking at rational functions. So, a rational function, what that is basically a polynomial all over a polynomial. So you have f of x equals p of x over q of x, and p of x and q of x are both going to be polynomials. So it's really just a function where you have a polynomial all over another polynomial. And so the most basic rational function with a variable expression in the denominator is going to be 1 over x. X is probably the simplest polynomial with a variable in it. So the simplest rational function with a variable expression in the denominator is going to be 1 over x. So now we're going to look at the domain of f of x equals 1 over x. And if we look at it, we can see that no matter what x value you put in, it's always going to work except for one x value, and that's at 0. And 0 won't work in this function because if you plug in 0 for x, you get 1 over 0, and anything divided by 0 is going to be undefined. It doesn't exist. So to write this as an inequality, that's going to be x is less than 0 or x is greater than 0. For set notation, you do that fancy looking bracket. We put x, that line which stands for such that x does not equal, sorry, it's supposed to be 0, not 1. And then close the bracket. So this says x such that x does not equal 0. For interval notation, it's going to be from negative infinity all the way to 0. Close the parentheses. You can put this big U, which stands for union, which is just another way to say or. And then from 0 to infinity. So our interval notation is from negative infinity to 0 or 0 to infinity. So let's keep on going. So now what we're going to do is we're going to see what happens to the function f of x as x is going to infinity. So without bound means as x goes to infinity and as x goes to negative infinity. So if you plug in all these x values, 1, 10, 100, and 1000, you get 1, 0.1, sorry about that. Let me write a little nicer. 0.01 and 0.001. So you plug in those x values into the function, that's what you get. And when x decreases without bound, so we have negative 1, negative 10, negative 100, and negative 1000. We're just going to plug these into the equation. You get negative 1, negative 0.1, negative 0.01, and negative 0.001. Okay? And if we look at the first table where x is going to infinity, we can see that f of x is slowly but surely making its way to 0. And at the same time, when x is decreasing without bound, as x is going to negative infinity, x is also going to 0. Okay? So we can see that the end behavior shows that this graph approaches but never actually touches or crosses the x-axis. And that is what we would call an asymptote. All right, the x-axis is an asymptote since the graph never actually touches or crosses it. All right. For the next paragraphs, we're going to see what happens as x approaches 0 from the positive side, from the positive direction, or from the right side, and also as x approaches 0 from the negative direction or from the left side. So when we say x goes to 0 from the right side, we write it as x goes to 0 with a plus right above it. And same thing here, as x goes to 0 from the left side. So when x is 0.1, we get 10. When it's 0.01, it's 100. And when it's 0.001, it's going to be 1000. So we'll plug in the negative version of those numbers into f of x as well. We get negative 10, negative 100, and negative 1000. Okay? So when we're comparing these two tables, we're not really comparing them, rather than looking at each one individually, we can see that as x goes to 0 from the right side, from the positive direction, f of x is increasing and making its way to positive infinity. And for the second table, as x is going to 0 from the left side or from the negative direction, it's slowly making its way to negative infinity. Okay? So what we see here is that the end behavior shows that the graph approaches, but never crosses or touches the y-axis. So that is what we'll call an asymptote as well. So we have two asymptotes for this rational function. for 1 over x is going to be the x-axis and the y-axis. So let's actually plot some points and see what this graph will actually look like. So if you plug in these x values, 1 over -2, that's going to be -1/2. -1 will be -1, and 1 over -0.5 will be -2. And for the positive values, we have 0.5. We get 2. 1 over 1 is just 1, and 1 over 2 is 1/2. Okay, so we have our 6 points. And before we actually start graphing these points or plotting these points, what we always want to do when it comes to rational functions is we want to graph our asymptotes first. So we talked about this in the previous slide. F of x equals 1 over x. We'll have an asymptote at x equals 0, or sorry, at the y-axis, and the x-axis will be a better way to say that. So we draw dashed lines to represent the asymptote. And once we do that, then we can plot our points and graph our graph. So let's go to the negative table first. We have -2, -1/2, so about right there. -1, -1, and -0.5, 2. So if we connect these dots, it should look something like that. It's going to be a little soft curve, curving like that. And for the top right part, or out of the right table, we have 0.52, 1, 1, and 2 and 1/2. So this will look similar, except it's going to be going the complete opposite direction. Kind of like it's mirrored over the origin. Okay? So from here, we can actually figure out what our range is going to be. If we look at it, we can see that every single y value will be hit except for 0. And if you look at the graph, that's because we can never have this 1 over x equals 0. It just doesn't exist. There's no x value that meets that. All right? And that's because there's no x value you can plug into this function that will give you an f of x or a y of 0. It just doesn't exist. So that means there's going to be an asymptote at that y value. So the inequality will be y is less than 0 or y is greater than 0, because it should hit every single real number other than 0. The set notation will be the weird little fancy brackets, and then y such that y does not equal 0. And for interval notation, we're going to have -infinity all the way to 0, union 0 to infinity. So that's our range for the function. We're in 3 different ways, but they all say the same exact thing. And now we're going to see where is f of x increasing. So remember, when it comes to increasing and decreasing functions, we read the graph going from left to right, because we have to read it with the x values increasing. So we start from the left side and we slowly make our way to the right and see how the y values react, or rather, are we going up or down? So if we start right here on the left side and we slowly make our way down to the right, we see we're actually decreasing the whole way. So the left side of the graph, it's never increasing. But now we're going to look at the right side. If we start at the left and we start going to the right, it's the same thing. We're just decreasing. Our y values are getting smaller and smaller. It's not increasing either. So that tells me that this function is never increasing. So where is f of x equal 1 over x decreasing? Well, you might think that might always be decreasing, but it's not. Just because we're never increasing doesn't mean the graph is always increasing or always decreasing, and that's because this graph doesn't exist on the x or y axis. Or a better way to say it, doesn't exist when x equals 0. So this function exists, or it's decreasing when x is greater than 0, or, an or rather than a comma. So x is greater than 0, or x is less than 0. Nothing happens on the graph when x equals 0, because that's asymptote, and we cannot put x into the function when x equals 0. So if it doesn't exist, it's not increasing or decreasing. So it's decreasing when x is greater than 0 or when x is less than 0. Now, is f of x equal 1 over x an even function, an odd function, or neither? It's an odd function. All right, and that's because an odd function needs to meet the requirement f of negative x equals negative f of x. And if we plug in, or rather if we solve for what f of negative x is for this function, it'll be 1 all over negative x. And negative f of x, if we solve for that, that'll give us negative 1 over x. and these two are the exact same. So that means it's going to be an odd function. So let's keep on going. Here we have our transformation rules. So we're going to start on the left side. We have A. Remember, A tells us if it's a vertical stretch or compression, and if it reflects over the x-axis or not. Our B term will tell us if there's a horizontal stretch or compression, and if there's a reflection over the y-axis or not. This one kind of moved, but the K value is a vertical translation. It shifts up and down, and our H value tells us if there's any horizontal shifts left and right, or horizontal translations, whatever you want to say. Okay? So let's go on to the table on the bottom. For the table on the bottom, we need to figure out what our new vertical asymptote will be, our new horizontal asymptotes, and our new reference points. So let's start with the vertical asymptotes. So for the parent, I don't say parent function, but for the function f of x equals 1 over x, our vertical asymptote happens at x equals 0. And it happens at that point because we cannot have a denominator of 0. So we need to carry that same logic into our new transform function, and we need to see when does the denominator of this function equal 0. Because when that denominator equals 0, that's when there's a vertical asymptote, because it cannot exist. And we can see here, if we set that parentheses equal to 0, we get that x has to equal h for this function to not exist. So there's an asymptote at x equals h. Because you plug in h, you get 1 over b times h minus h, which is 0. So you end up getting 1 over 0, which doesn't exist. Okay? Now for the horizontal asymptote, y equals 0 is a horizontal asymptote. That's because 1 over x, the whole fraction, can never equal 0 because the numerator is just a constant term of 1. So there's no x values that will set 1 over x equal to 0. Okay? So we're going to carry that same logic into our transform function as well. And we need to see, or rather, we could see that this whole fraction part right here, the a times 1 over b times x minus h, that can never equal 0. Unless a equals 0, but we don't deal with a equals 0, we're not going to worry about that. But rather, when 1 all over 1 over b times x minus h, that can never equal 0 because the numerator is a constant term of 1. So this transform function can never have a It can never have a y value of k. And that's because that whole parentheses that I've circled can never equal 0. So if we set that equal to 0, then we know g of x or y can never equal k. So next, we're going to see our reference points. For our reference points, you could just memorize it and know that our reference point -1 will be negative b plus h, comma negative a plus k. And our reference point 1 will be b plus h and a plus k. You could memorize both these individually. I personally don't recommend it. I think it's a better use of your energy to memorize the complete transformation rule, b of x plus h, comma, a of y plus k. Because you can plug in either of these two reference points and still get the same thing. So I think it's better to just memorize the complete transformation rule, b of x plus h, comma, a of y plus k. And you just plug in your reference points into that and still get the same exact thing. So let's keep going. We have our transformations now. Actually, what I wanted you guys to do before I switch the slide was for you guys to actually pause the video and try to do it yourselves. And I'll show it and go over it together. I show you guys number 1 and number 2, but I do suggest to pause the video and try out number 3, number 4 by yourselves. Okay. So let's go over number 1 and number 2. Then we'll go on to 3 and 4. So number 1, we have 1 over x minus 3. That tells me my h value is 3, so it's a shift to the right by 3. 1 over x plus 3 is a horizontal shift to the left by 3 because h is negative 3. For number 2, we have 1 over x minus 3. Our k value is negative 3, so we're going down by 3. And 1 over x plus 3, k value is 3, so we're shifting up by 3. For number 3 and number 4, for number 3, we have g of x was 2 times 1 over x. Our a value is 2, so the vertical stretch by 2. For the second one, our a value is 0.5, so it's a compression by a half. For the third one, we have a reflection over the x-axis and a vertical stretch by 2, since our A is at -2. And then for the last one, we have a vertical compression by 1/2 and a reflection over the x-axis, since our A is -0.5. Okay? And now for number 4, the first one for number 4, we have a horizontal stretch by 2. That's because our B value is actually 2, since 1/2 gives you that 0.5. For the second one, our horizontal compression is 1/2. That's because 2 equals 1/B, or B equals 1/2. So B equals 1/2, you have a horizontal compression by 1/2. For the third one, it's a reflection over the y-axis, since it's a negative, and it's a horizontal stretch by 2. And for the last one, it's a reflection over the y-axis and a horizontal compression by 2. Sorry, my handwriting is not very good. It's a horizontal compression by 1/2. Okay? So let's keep going. Now we're going to go over an example of how to actually graph a transform function with a g of x. So here, the first thing we're going to do is we're going to figure out what our transformations actually are. Our a value is 3, our b value is 1, our h is 1, and our k is 2. Right? K, h, a, and there's no b value. So it's just going to be 1. So our transformations will be a vertical stretch by 3. We'll shift to the right by 1. And then we'll shift upwards, or translate upwards, whatever you want to say, by 2. And that's from our k value and our h value. Okay, so now what we're going to do next is we need to actually figure out our asymptotes and our new reference points. We can't really graph it if we don't know what our asymptotes or our reference points are. So actually, I kind of missed something. We're going to do that transformation rule up top. So our transformation rule, remember we talked about that a few slides back, is, sorry, not a of x, but b of x plus h. B of x plus h, so that's a little sloppy. And a of y plus k. So in the context of this problem, our b is 1, our x is just a variable, our h is 1, so we have x plus 1, and our ay plus k, our a here is 3, our y is our variable, and our k is 2. So it's x plus 1, comma, 3y plus 2. So for our vertical asymptotes, for our parent, not our parent function, but for the function f of x equals 1 over x, it's x equals 0. And that's because, like we said before, it's the denominator. And our vertical asymptote for our transform function for g of x will be x equals 1, since that is what turns the whole denominator into 0. Or in other words, it's our h value. For our horizontal asymptote, for the f of x equals 1 over x, that's y equals 0. But for our g of x, our transform function, it's going to be what g of x equals, or what y equals, when you set the whole fraction part equal to 0. So in this case, it's just going to be 2, or in other words, your horizontal asymptote will be your k value. For our reference points, we're going to take them and plug them into our transformation rule we wrote on up top. If you like to memorize the rules we talked about a few slides back, you can. I'm just going to plug them in and do it that way. So -1 plus 1 is 0. And then -1 times 3 is -3, plus 2 is -1. Next, we have a reference point 1, 1. We plug that in. We get 2, comma 5. Right, 1 plus 1 is 2, and then 3 times 1 is 3, and 3 plus 2 is 5. So now that we have our asymptotes and our reference points, we can go ahead and graph this function. So first thing we do is do our asymptotes. So x equals 1 will be right here. We do our dashed line, and then our horizontal asymptote, y equals 2, will be right there. Now we'll plot our reference points. We have 0, -1 right over here, and 2, comma 5 right up there. So we know roughly what it should look like, so we can sketch it. Completely miss the point, but it will look roughly like that. And same thing here. I actually hit the point that time, and that's what this graph will look like, more or less. Okay? So now let's go over the domain and the range. So the domain, remember, the domain is all possible x values, and we can look at the graph and see that we get every single x value except for when x equals 1, because that's our asymptote. So our inequality will always be x is less than your h value, in this case 1, or x is greater than your h value of 1. For set notation, we can just rewrite that through the bracket, x such that x doesn't equal 1. And for our interval notation, it'll be from negative infinity to 1, union 1 to positive infinity. And for our range, we can look at the graph and see we get every single y value except for y equals 2, since that's our asymptote. And so we can write our inequality as y is less than our k value, or 2, or y is greater than 2. We can just rewrite that in set notation. So y such that y does not equal 2. And interval notation from negative infinity all the way to 2, union 2 to infinity. Okay, so that's number 1. I know I did it a little quickly, but if you need to rewind the video, please do so. Rewatch it, see what I did. And I want you guys to actually pause the video now and try number 2 on your own. In a couple seconds, I'll go on to the next slide and show you what you should have got. Okay, and here's what you should have gone for number 2. Your A value is 1, your B is 1/2, H is -3, and K is -1. Your transformation rule should have been 1/2 x minus 3, comma y minus 1. Your vertical asymptote would have been x equals -3. That's your H value. Your horizontal asymptote should have been -1. That's your K value. Your reference points, if you put it into the transformation rule, you would have gotten -3.5, comma -2. And if you plug in 1, 1 into your transformation rule, you would have gotten -2.5, comma 0. And if you look at the graph and you figure out your range will be x is less than -3, your h, and, or, sorry, not and, it should be an or in between, or x is greater than -3. And that's what you get for set notation and for interval notation. And for the range, your range should be x is less than -1, or, sorry, y is less than -1, or y is greater than -1. And that's your k value, so it's every value except for k. Okay? So guys, hopefully this video helped. Hopefully you learned something, and have a nice day.